Hello everyone. So in the last class we did mostly post installation calibrations of industrial robot, mostly mastering of robot joints we did. We also did TCP calibration, TCP tool center point, origin and orientation calibration that we have done. So let us quickly look to this module, what we'll be doing in this module. This module is about calibration of industrial robot systems. Basically that is the systems which are associated with robots and its functioning in the workspace when it is implemented in the industry shop floor. So it is surrounded by many other automatic devices and systems which make robot to do its function well. So let us quickly look what we are going to do in this class. Okay, so this was our post installation calibration task we did with the industrial robot, that is mastering of robot joints, TCP origin calibration and TCP orientation calibration that we did in previous class. Okay, so in this module we'll be doing calibration of industrial robot systems that include work surface calibration. We will be doing this in this lecture, that is today's lecture, that is 3-point calibration and indirect method. We'll closely look at those techniques, and we'll be doing external fixed tool calibration, that is any tool if it is mounted in the workspace and robot is holding the object maybe that it needs to be machined. So how to handle that kind of environment where tool is outside and the tool object is with the robot. So that kind of calibration we'll be looking at in second lecture of this module. And dynamic systems, that includes robot mounts, like a linear mount on which a robot can be mounted, and robot from the base up itself will be mounted on top of it and it will move on the linear rail. Okay, so there are calibration issues which are involved with that also, that we'll be looking at in lecture 3 of this module. We'll be also looking at rotary turntable which are there in the workspace that can run sync with the other joints of the robot. Normally they are controlled with the industrial robot controller itself, so that becomes the 7th axis. So all those issues we'll be looking at in lecture 3. Okay, so let us move ahead with work surface calibration, that is today's lecture. So yes, so what is work surface calibration? A coordinate system with origin is assigned to the work surface. Let us say your robot has to work on a surface which is nearby. Instead of having a horizontal flat table, even horizontal flat table is a work surface. Different kinds of objects which may be placed on the table itself, and the robot is supposed to do pick and place task, or it may have to do some array type of job. So all those kinds of job requires work surface calibration. It is easy to do if it is calibrated well. You know the frame which is associated with the work surface, so that you can put the object with reference to the coordinate system which is there on the table itself, on the work surface itself. It should not be referred with respect to the robot base. It will be very difficult to assign that coordinates, and also it will be difficult to understand the coordinate because it is a big robot. Most of the time it becomes very difficult to estimate where my object is, whereas it is very easy if it is kept on the table with respect to the table coordinate system or work surface coordinate system. Okay, so that is what is work surface calibration. We'll try to assign a coordinate system. If it is a coordinate system, let us say it is attached at the corner of this table, you can have an array of objects which are kept on this work surface. Okay, and each one of them is referred with respect to the origin which is placed here. So you need to place an origin with respect to the robot base. So that is our job in today's class, and there are different techniques to do it that we'll be following. And TCP can now be jogged. So you can jog the TCP along the axes of this work surface. If I say move along X of the work table, so you can your robot goes like this. You can make it move like this. Got it? So in different axes which are along the axis of the work surface, the robot can be jogged or it can be programmed. You can move along the edges of this work surface. Okay, so it is a capability which is very much required in order to program it conveniently. Okay, So if you move with respect to the robot's base or with respect to the tool, it becomes very difficult to precisely locate just by jogging, okay, which is very much required while programming. Okay, so points can now be taught relative to the work surface, and if the work surface moves, whole of this panel, this work surface moves, so there is a provision, most of the robots they have it, you just need to say how much it has displaced, okay, how much the orientation changes you have done, okay, so that the delta changes you can just put it to the robot system, robot controller, robot teach pendant environment, so it quickly understands where is my new origin and how it is now aligned. Okay, so by introducing the offset, entire set of taught points which are relative to the work surface frame, okay, so that gets moved. So it eliminates any need for reteaching of those points. So it doesn't need to reprogram if at all objects are placed on the workspace. There are two common approaches to do this job. One is 3-point method, other one is indirect method. We'll start with 3-point method now. Other methods could be just like our tool calibration we did. You can get this information from the CAD if it is there. Okay, so yes, if you have a CAD which tells this distance, this position vector and the orientation vector of this frame with respect to the robot base, you can quickly do, and you don't need any sort of calibration. But it is not very much advisable to do this because it is a good distance. Even a small amount of error will cause your robot tool tip to hit that surface. Okay, so that is quite probable because this is long and your error is relatively, it is smaller with respect to this distance, but it may be quite big as far as your robot's accuracy is concerned. Okay, so it can hit that. So it is not advisable in case of this. Okay, so let us start quickly on 3-point method, how it actually does that calibration, how it actually finds out the orientation and position of your work surface with respect to the robot's base, that is work surface calibration. Okay, so basically pre-calibrated tool is mounted at the tool flange of your robot. Okay, it is mostly a sharp tip which can be pointed on any location where you wish. Okay, so that is the first job. So after doing this, this TCP is calibrated already and your robot forward kinematics can quickly find out the tip of your tool location with respect to the robot base. So this is the first thing that you have to do. Next, the TCP is now moved to the origin of the work surface. First thing that you are going to do is you are going to place it at the origin of the work surface. So if this is your work surface, so you want to make this point as an origin, just take your TCP of the pre-calibrated tool to that particular origin. Next task is now the TCP is moved to a point on the positive x-axis of the work surface. Again, this is intended positive axis, okay, where you want your x-axis positive to be. Okay, so this was your origin, so this is your direction. So anywhere you can take your TCP to on this axis. This is one of the point that you can put it. Next, the TCP is moved to any point on this plane. If this is a XY plane, so your tip can touch anywhere on that surface. Okay, so one of the point you have to take your TCP to. Okay, so these 3 steps are involved. First step, you have to put a pre-calibrated tool, or if you have just put a tool, you can calibrate it. That is first task. Next, you have to touch this origin. Next point is you have to touch one of the points on the x-axis positive direction, and your final step will be touch your TCP to one of the point on XY plane of the work surface. Okay, so using these acquired points, the origin and orientation of the frame which is attached to the work surface is calculated by the robot controller, and that is what we are going to learn today, how actually it does it. Okay, So let us begin with that. So how many unknowns which are there? Position of the frame is unknown. So that is 3 unknown is there, x, y and z. And similarly 3 orientation unknowns are there. That is rotation can be there. Okay, so that is also to be defined. So 3 plus 3, that is 6 unknowns are there. So how many inputs does it require? Input variables that does it require? So first thing you are doing, you are taking it to a point. So you are ultimately taking it to the origin of the work surface. Okay, work surface frame. So it is 3 inputs that you are giving, that is x, y and z of origin. Now you are taking one point on the x axis. So one variable is there. Okay, along the constrained x axis. So it is just one variable you are taking it to, that is there. Got it? Second one, when you are taking it to xy plane, it is basically 2 remaining variable which are defined here. So total variables are 6 here. So it becomes a solvable system and your robot controller can solve it. Okay, so let us do it ourselves also. So the TCP of the pre-calibrated tool moves to the origin of the work surface. So this is the first thing that you did. Okay, so what it actually did, it calculated this position vector. So what is that position vector? It is a vector which connects robot frame and the frame that is attached to the work surface, the origin of that. Okay, so that location is, so it is Rx, Ry and Rz. So that point is quickly assigned to this origin. Okay, how is that point calculated? It is calculated using the forward kinematics, because once you take your pre-calibrated tool to this location, that means using the joint angles, using the dimensions, using the DH parameter of all these will let you calculate this quickly. Okay, so that is how R is now known. So after the first step, what you have in hand is R vector. So that is basically the position vector of the origin of the work surface frame. Okay, now the second step. So the TCP of the pre-calibrated tool moves to a new point, that is T2, which is on the x-axis of the positive x-axis of the work surface. It is somewhere over here. Okay, so you took it here. Got it? Now again what you did, using forward kinematics, you can calculate how much is T2. So T2 is known because you made your TCP touch to that location. So using your forward kinematics, you can calculate T2. You already had R in hand, that is origin B on the work surface was known. So R is known, T2 is known. So you can calculate U vector. What is U? U is a vector which is aligned along positive x-axis. So that is U. It can be calculated using simple vector triangle which is here, U, R and T2. So that is quickly done. So unit vector that is along x-axis can be calculated as U by magnitude of U. So that gives you unit vector along positive x-axis. From the origin, this is your x-axis. Okay. So anytime we are taking our TCP to any location, we use forward kinematics to calculate that tip location. So that is very easy. Okay, the third step, the pre-calibrated tool TCP now moves to a point T3, which is in the XY plane of the work surface. So if this, you are assuming this is positive Y, it is going to be, so you have to remain in this plane somewhere. Okay, so it is robot tooltip is now taken to this location. Okay, now what do you get? You immediately can obtain T3 using robot's forward kinematics. R was already known, so now you can calculate a vector V. What is V? V is a vector in XY plane which is given by T3 minus R. The way we calculated U, exactly in the same way we can calculate V. Okay, but V is not aligned with y-axis or x-axis. It is just a vector which starts somewhere over here and it ends anywhere on the xy plane. So this is your v. So altogether u and v lies on a plane which is xy plane. Okay, so now quickly you can calculate a vector w which is along positive z axis by taking the cross product of u and v. If you take cross product of u and v, which is lying, both of them are lying in the xy plane, so you get a vector which is perpendicular to that plane, so that is w. So any vector which is perpendicular to xy plane will be aligned with z axis, positive z axis. Okay, so if you take it u cross v, it is positive z axis. Okay, so you got what? You got w. Now I am ready to find out my unit vector along z axis. So that is nothing but w by magnitude of w. So you got what? You got z. So you have obtained now a z vector, unit vector, which is aligned along positive z axis. Got it? So that is found out. So now you know unit vector along x axis, unit vector along z axis. So you can quickly find out unit vector along y axis by taking cross product of z and x. So this was your unit vector z, this is your unit vector x. So taking cross product like this will give you a unit vector along y axis. Okay, so that is your bold y small. Okay, so again I am using TCP location T3 found out by forward kinematics. That is now quite trivial. Okay, so you got all the axes. You got x, that is through first step. You got y now. As soon as you contacted here, you found out z and finally y. So all the three unit vectors which are aligned along x, y and z axis of your work surface frame. So you now know that. Okay, so all x, y, z are now known. Okay, and you also know r. This r you got to know at the first instant when you brushed it here. The TCP was brushed over here. Okay, so r is known, x, y, z vectors are known. So now the rotation matrix of frame B with respect to the robot base may be given as this. That is projection of x vector along your robot frame, because you know these are the vectors which are expressed in frame R. Okay, so x will have component along I, j and k. So you will have x component along I, x component along j, x component along k. So you will get this, this and this column, and similarly y and projections of y, all the projections of y will go here, projections of z will go here. All together it makes it a rotation matrix. What type of matrix is that? It is rotation of frame B with respect to the robot's frame, that is this frame. Got it? So you quickly got the orientation matrix of frame B. You already had what? R. Okay, so this R was already known, given by Rx, Ry and Rz, that is projection of R along x, y and z. Okay, so everything is now known. So any point, if it is there with respect to this frame, okay, so that is xb, yb and zb, which is expressed in workspace frame B, can now be quickly converted to the robot's frame by multiplying the orientation matrix. That is the first transformation that you do. Okay, that is the rotation transformation, and then you do translation. That is, first you have to rotate and then you move it to the new location. So any point, if it is in this frame, so you have to do these two transformation, and you can calculate that point with respect to the robot's frame. So if it is in this frame, you can calculate the same point in this frame. Okay. So if it is in robot frame, now you can do inverse kinematics quickly and you can make your robot go to that particular location. So any point you get in hand which is expressed in the frame B can now be converted to the point in the frame robot, in the robot frame, and you can do inverse kinematics and you can take your robot there. Not just inverse kinematics, can be any other control approaches, you can take your robot there. So that is how it works. Okay. So this is the first way of doing calibrating your work surface. Okay. So now we'll look at other method, which is an indirect method. So in this case, why this is useful? It is useful when the origin of the work surface is not accessible. Sometimes origin may be not reachable by your robot itself. It is quite far off. Okay. So that is not reachable. And sometimes it may be occluded by some fixture in the workspace, or it is out of the plane. Your edges are not straight towards that end. So forget it. So you don't need the origin now to be brushed with your TCP. This method is very simple. What it says, your TCP can now be moved to 4 accessible points. Any 4 point in the workspace which is accessible to your robot. Okay. The coordinates of which are known with respect to the work surface frame. This is the prerequisite, that is the condition which is here. So all the points that your robot is now going to brush, those coordinates should be known with respect to your work surface coordinate system. Okay. So you have to brush it to the 4 locations. So that is there. Unknowns for the work surfaces, 3 for the frame position and 3 for the frame orientation. Same way we had it earlier. So how many inputs you are feeding is 4 points. That is Pi, x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4. I varies from 1 to 4, and I can arrange all the points in this manner. So it's a capital P arranged in a matrix way, like x1, y1, z1, 1, x2, y2, z2, 1, and similarly x3, y3, z3, 1, x4, y4, z4, 1. So this becomes your P matrix. So what is this matrix? It is nothing but all the points collection. So you can handle all the points simultaneously through any transformation matrix. So this is what I am just creating over here. Okay. So now this is what? This is position vector, positions of point. All the points on the surface in frame R is obtained by moving the TCP to all the 4 locations. So now what you did, you simply took your TCP to those known locations. Okay. In 4 steps, you have taken your robot to all those locations. Because the robot already had a pre-calibrated tool, so you quickly obtained what? Those locations in the robot's frame. So now when you brushed your TCP to all the 4 locations, so points on the surface in frame R is obtained. That is the robot's frame is obtained. Okay, that is using forward kinematics. So 2 things are now known, that is same points in robot's frame and same point in your base frame, that is your work surface frame. Okay, so both the things you have in hand, what you need is a transformation between them, that is the unknown now. Okay, so this is already known. So now this was known already, that is the point in its own frame, that is the work surface frame. This is what? This is the point in robot's frame. Okay, so that includes 2 transformation. You have to transfer this point from the base frame, that is the work surface frame, to the robot's frame. How that is done? This is your unknown transformation matrix that can do this, that you want to identify here. So it consists of a rotation matrix first, and then this is the translation matrix. Okay, so these two were the unknown earlier in your previous method also. That is what we want to find out. So this becomes unknown, so you can quickly take the product and find out T together, okay, in terms of variables, okay, and you can find out that T using those variables can be quickly found out by taking inverse. You have to bring this here, taking inverse, and this was already there. This was already there. You brought it here, taking inverse, and you can find out the unknown transformation that can take you from your base, your work surface frame, any points on the work surface frame, it can bring it to your robot's frame. So that is what you wanted to know. This is the transformation matrix. A combined transformation matrix can now be obtained. Okay. So that is how any point now, if you get in hand, you can quickly use this transformation matrix and convert it to the robot's frame, and now robot can be programmed to go there very easily. Okay. So that is how, and before I move ahead, I'll show you some videos which are applications of this. Okay, so that was due from the intro part only, so I'll just quickly show. So this is an application when a robot is trying to create an array of cubes. Okay, but the cubes are now to be put in a coordinate system which is there on the table. You see the cubes are aligned with respect to the frame which is there on the table on which it is skipping. Okay, so that is an array of cubes. It is quickly taking all the pellets from the location which is a taut location. So those are the locations which are there with respect to the robot's frame. Okay, and it is putting all the pellets to the frame which is there on the work surface. So the final cube now will go on top of that, and done. So this is one tentative application. There are many such pelletizing tasks which are there in the industry. So this robot, it is using a vision technique to find out the pellet location on the table. It is picking it up, correcting it, then it is inserting in a hole which is now again in a frame which is attached to this work surface. Okay, so it is inserting it. It will pick up another one and again put it. So this is yet another application when the workspace is vertically placed. Again it is using vision to find out those pellets and correcting it. It will correct it. Pellets are lying horizontally, so it is picking up like this and then correcting it properly so that it can be inserted to the hole. Got it? So this is another very good example when you require such work surface calibration. So yes, this is there, and let us just quickly discuss how many minimum number of coordinates which are required to fix the origin in 3D space. This is a small discussion that I want to have because we will be dealing with similar techniques later on as well in this module. So let us first clarify that these are some fundamentals that you need to know. So let us say if I have just one point, okay, so where your origin can lie? Your origin can lie anywhere in the workspace. So you can have infinite location for your origin. So one point is not enough to constrain your origin. So you can have anywhere in the 3D workspace. Okay, so that it is not enough, you see. Now I'll do another thing. I'll just add on one more point. Okay, now I have a line segment. So if these 2 points are defined in space, so where your origin can go? Any idea? So yes, your origin can lie if at all this point is at a distance r1 and it is distance r2 from the origin, so your locus of your origin will be somewhere on the circle which is like this. Okay, so there is a equivalent radius which will go there, and that about which your whole of the origin can be located anywhere on this. So you can have infinite number of vectors which can be there that bears the origin, and it can tell you the same coordinates. So your origin is still not located properly. So 2 points are not good enough. So now again I'll try to put yet another point in the workspace. So again I have put yet another point in the workspace. This time you have 3 points. Is it enough to state your origin, where your origin can go? So yes, let me draw that. Okay, triangle which is formed using this. So a set of 3 points are very good enough to define your surface, but your origin, is it constrained still? So it can go on the any side of your plane which is defined using these 3 points. So your origin can be here on the upper part of the surface, or it can be somewhere behind the surface. Okay, so this can be R1, R2 and R3. From the other side also you can draw similar 3 vectors which are R1, you have R2 and R3. So still your origin can have at least 2 positions. So even 3 points are not good enough to define your origin. Okay, if it is freely defined in the work surface or on the workspace of the robot, your origin is still not constrained. So finally, as soon as you put your fourth point, 1, 2, 3 and 4, your origin is fully constrained. Mind it, it has a singular solution. This one of the points should be off the plane. Okay, otherwise you will get a singular matrix for this and it becomes not solvable. So if these 3 are in plane, it will define your surface. So distance of this origin, the way you constructed, origin can go here, origin can also go there, but if it is off the plane, so you cannot mirror your origin about that plane. So immediately you will see a difference in distance if it is taken from both the new origin location. So only one solution is now possible. So that finally fixes your origin location. So that is why 4 points minimum is required for the method that we followed at the end. Okay, that is when origin is not accessible, you have to take minimum 4 points to define your origin, and using the orientation, that is the normal to the surface, you can find out the direction of your frame also. So yes, and the location, one of them can become origin and whole of the origin system can be defined. So this is very, very fundamental, you should know this. Okay. So yes, that's all for today. In the next class, we'll be dealing with fixed tool calibration. If it is a tool, it is not an object that robot is handling. Your object is now holded by the robot and your tool is mounted somewhere in the workspace, and you are trying to machine your object using that tool which is now fixed. So how to calibrate that? So those type of application I will show. So let us quickly see some of the calibration demonstration. What is the result of today's calibration technique? So this is one of the way where this base, which is red cuboid that you can see, the top surface is now calibrated. My robot can now move along the edges of the cube which is there in the workspace of the robot. It is moving along one of the axis, that is the edges, along the edge of this cuboid. It goes to the origin now. So this was Y that it covered immediately. It was Y that it did now, and then it is along X it is moving. It is along Z it is going. X, Y and Z. So you see your robot can now move in a frame which is attached to the work surface. So top surface of this cuboid that you can see is your work surface. Okay, so that is the advantage of having that. Now let me show you yet another video. In this work surface, your robot can now orient about the axes also. It is a combined orientation that I am trying to make. So about any point, now your robot can make a tilt and roll kind of thing. So once the work surface is calibrated, you can position or you can orient with respect to the frame which is attached to the work surface. So that is what was the message of today's lecture. So yes, that's all for today. In the next class, we'll be dealing with fixed tool calibration. What is that? Your tool is mounted in the workspace. It may be a simple grinding tool that is rotating and you are holding the object using your robot's gripper. Okay, and you can take it there, you can machine it. So now the tool is not mounted with the robot and object is stationary somewhere in the workspace. It is otherwise, it is other way which is there. So you have tool which is there and your object is held by the robot. There are few applications that you have seen in the application video in our very first lectures. That was introduction to the robots. So you saw it was an adhesive operation, gluing operation. When adhesive dispenser can be stationary and your object was holded like this and you can do that kind of motion. Hope you remember it. So yes, that's all. Thanks for today. That's all.